Okay, welcome back to the Geotechnics lab, everyone. This is the fifth video in the series, and we're going to be looking at shearing our sample in this episode. So, I think the best way to go about this is to start from the process of, we've just finished consolidation, and now we're going to look at shearing. There's a few things we need before we start the shearing process, and we'll take a look at them in turn and talk around the subject as we go. So the first thing we need is to find our shear rate. Well, the main thing we need to do is to find our shear rate. This is the rate, as I previously mentioned, at which the loading ram is forced into our sample. You don't want it to be too quick, and equally you don't want it to be too slow. You don't want it to be too slow just out of pure well, just organisation and sort of having to wait for that length of time when you don't really need to. Equally, you don't want to have it set too fast, otherwise your sample won't shear in the correct fashion. Your pore pressures will not dissipate in the correct way, and it's something you generally want to avoid. So we use this formula here that's provided by the standards. Vmax is equal to the height after consolidation multiplied by the strain, or the final strain at failure, this factor F over 4 and T100. And to do that we need a few things along the way. So firstly, let's have a look at calculating the height after consolidation. I mentioned at the end of the previous video how we can't measure intrusively the height of our sample, so we need to use the data and the information we have available to us to come up with a good approximation for this value. Now, if you think about things fundamentally, we have an isotropic sample that's been loaded it's been loaded isotropically, where sigma 1 is equal to sigma 3. Now, realistically, as we have a volume change out of our sample, we should be able to quite easily calculate the change in volume as it refers to a change in height of our sample. And this equation is provided within the standards, and it sort of makes sense when you think of it in the isotropic sense. For an anisotropic, that is loading condition where sigma 1 does not equal sigma 3, then you'd use a different factor. But for isotropic stresses, this value of F, or this Greek symbol for F, is a third, relating back to your sigma 1 plus 2 sigma 3, or sigma A plus 2 sigma R equation for your confining stress. So let's use this equation to find our height after consolidation. We know the height of our sample initially, that was before we started consolidation. We need to find from our data the volume before we started consolidation and the change in volume through consolidation, and that will give us an approximation for the height after consolidation. So let's take a look at our data. Here I am back on the same spreadsheet I was sort of using last time. I've made a couple of adjustments to it, and I've already done the calculations, and I'll uncover them as we go, just so you can tell. So the initial volume I've taken here to be 135,000 millimeters cubed. This value is taken, if I go and find it briefly, whoops. This value is just taken at the point where consolidation starts. So I've taken it at this value where P dash is approximately 50, but it soon rises after that up to a P dash of 150. I set it a bit further backwards just so just to give a good approximation of what the volume was before. Under an effective P dash of 50, as it was for a very long time, the volume changes were very small. So I've taken that as my initial volume, and then the final volume is 142,000 millimeters cubed. Again, that's the volume in the reservoir rather than the sample, but Because the water can only flow out into the reservoir, we can use these figures. This number here is just the is purely the volume at the end of the spreadsheet. So then subtracting those to find delta V, you get 7,007 millimeters cubed of change. Normalizing that by the first volume, the initial volume, and then multiplying it by a third, our factor F there, gives you this number, and we can return that to our equation with the initial height, all of these numbers put together, and you can find the height after consolidation is 74.68, well, 74.7 millimeters. So that's the new height of our sample. So if I just write these numbers in here, 74.7 millimeters, just for completion's sake. So the next thing we need to do is work out V max. This figure here, one thing we need to do along that way is get T100. Now we have height after consolidation, and to do that we need to use the log time method. If you think back to if you studied at the University of Nottingham third year soil mechanics, third year geotechnics, where consolidation is taught, the log time method is a way for calculating T100, approximating T100 and T50. So let's go into our consolidation data and have a look at doing that. Again, I have already plotted this stuff. Here you see a plot for the consolidation data when P dash was increased to 700 kPa. So that is the final and the biggest loading of our sample, up to a P dash of 700 kilopascals. And here I've done, as is the method, to draw a asymptotic, or a parallel line next to the linear phase of the primary consolidation, or primary settlement curve, and another parallel curve to the secondary compression or creep phase. And the point at which they cross over is T100. You can go in and look at lecture notes like the ones we have here provided, and these were my third year notes. Others are available online that you can use. So just to remind yourself of that. So if we read off this crossing point, we get T100, and T100 here is found to be 3,000 seconds. So I've used that in our equation to find V max, which is 0.107. And that V max is in millimeters per minute. So if you are watching carefully, you'll note that this number here, 50, is merely 3,000 divided by 60, because I want the time in minutes. We set our shear rate in minutes just for the ease of use. If this was in seconds, it would be a very, very small number, and not particularly helpful to visualize or use. It's far easier to compare in millimeters per minute. So Vmax, we've found out, we've used our value of 15% strain. This value, 15% strain, I've referred to it up here and down there. 15% strain is specified as the point where you can finish shearing in the standards. If we flick back to those, we have here the actual strain at which the test is to be stopped has not been specified, where here it hasn't. The test may be stopped when the strain reaches 15%. Or there's some other conditions there about deviatoric stress. But we'll use the 15% strain. So that's the number I put into my equation. So we're happy with that. Let's also just briefly talk about how we might think about when has our, if we go to 15% strain how can we be sure that our sample has reached a critical state? Just thinking briefly about critical state soil mechanics rather than the practicalities of testing soils in the Triaxial experiment. There are two ways in which you know two ways in which you might know that a sample has reached a critical state. The first way is when there are no more volume changes. Here we're doing an undrained test. That means we're going to close off these back pressure valves. In fact, we may as well do that now because we won't be changing our pressures anymore. So no water can flow out of our sample. The volume of our sample can't change. So we can't really use that as a condition to understand when our sample has reached a critical state. What we can do, however, is monitor our pore water pressure changes. When the pore water pressure becomes stable, as in there is no more change in pore water pressure, that's when you know that a slip plane has formed and you have reached a critical state. You're just moving down the critical state line, and you aren't affecting any change in the volume of your sample anymore, or the pressures inside your sample, the pore water pressures inside your sample. So that's how you might detect in your data when you come to analyze this, and I'll do another video briefly looking at sort of the analysis of this data, where you might know that, okay, this is the point at which we reached a critical state, and you'll need that for your critical state frameworks when you come to match up, perhaps where your sample has crossed onto your M line in QP space, where it's left the yield surface and moving towards the critical state line in QP space. Okay, so Vmax here, let's write this in as 0.107 millimeters per min. That's good. The next thing we need to do is go in and edit our software and put all these parameters in and get ready for testing. So one thing I'm going to do here is I'm going to open up the controller window. It's fairly familiar to what we've seen before. I've clicked onto the Undrained shearing tab, and in here we see three graphs. We've got the pore pressures displayed here, the force over time, and the displacement. Let's put in our speed, and then we'll talk about a few of the practicalities with doing this test. So 1.107 millimeters per minute. I'm going to set speed there. So we've got these two graphs here of force over time and displacement. Now, you might think on first looking that that is just the soil parameters, or those are displacements of the soil or the force on the soil. It's obviously not, because we can't intrusively measure those things. We have our sample sealed within a pressurized water cell, and we also have it covered in a membrane and top cap and all other such things. So the load cell here is measuring not the force on the sample, but the force on, this is the tip of the load cell here, it's just the force on this ram. Likewise, the LVDT that's measuring the displacement is measuring the displacement of this, the top of our cell here. If I move my displacement transducer up, you'll see that the displacement has shot up there, and that really has not done anything to my soil. So we need to be careful about when we use this, when we use these bits of data. We need to make sure that when we go and analyze it, we're taking data from the correct point and something to something that is relevant to us. So we need to go through a phase of what's called docking, and this phase is really about making sure that our sample top cap is sitting within our loading ram. The top cap there is shaped in such a way with its rounded top to meet up exactly with the load ram. if I was to draw this out, the load ram is likewise is shaped in the opposite fashion, so that you have a good seal and an even load distributed around this load ram, so that it's not leaning to one side or anything, and it's completely perpendicular, hopefully, to the top of the sample. Now, our sample, you might be able to tell, doesn't exactly line up with our load ram there. It's not actually sat inside the middle. It's very difficult when you go and think back to our preparation phase, way back in the first video, to know that you've got that exactly upright and level, so that your load ram will fit down onto your sample exactly at the right point, and evenly all the way around. We know from this, we can just look at this and think instinctively, well, as that load ram starts to sit onto our top cap, the sample is going to be moved around in different ways in our sample. It's not going to be loaded purely from the top in this primary stress sigma 1. So we need to think about the data that comes out of this, and perhaps say, well, we want to detect when the soil is actually being loaded. So there are two things we need to do. When we start our sample shearing, I'm going to click this frame up button, and that will start this load frame moving up at a rate of 0.11, near enough, millimeters per minute, and our sample will be pushed into the load ram that's fixed here. The load ram is sort of in a fixed position, our sample is going to move up into it. As that happens, the displacement's going to change, and we need to think about when we are going to stop our sample. Do we want it going all the way up to the top? We've said we want to stop our test at 15% strain, so let's consider what are we going to tell our controller to stop shearing our sample at. So we know our height after consolidation, we know the height of our sample at the moment. We can use that number in tandem with our final shear strain value to find an approximate height of our sample after it has been sheared. It all being equal, and we'll instill some leeway into this, just so that we do go past 15% strain. But there's no reason to go too far past it, because ultimately the test should be stopped at that point. So the height after shearing I've found here with this formula as being the height after consolidation times 0.85, and from that you can find this change in height, or change in displacement really, because it is the displacement of the load ram into our sample, of 11 millimeters. So if I was to set a maximum displacement, I could set from this point, as we have it here, 11.2 millimeters from now. But obviously our sample isn't going to start loading or actually being sheared until the top cap is fully seated within our load ram. So we need to add on some displacement to that. Also, it's worth noting that these LVDTs have a maximum stroke of 21 millimeters. So you can't go past that anyway, otherwise you'll start to damage your own equipment. So what we'll look at is, once we've started shearing and we know that our sample is seated within the load ram, I'll come back and I'll change our maximum displacement, and I'll tell the load frame to stop displacing our sample after whatever number it is reached in our displacement, this displacement and the maximum displacement number here being the raw value from the LVDT. It is not anything to do with our sample. So once, to clarify and to make it a bit simpler, once the loading ram here has the top cap fully seated inside it, it will have some displacement. At that point, I will then go and add on this value of 11.2. So one other thing we can do as well is we can roughly calculate our time to shear. We have a shear rate, and we can multiply that or divide that shear rate by our time our height of shearing, our change in height after shearing. So all I've done here is multiplied this number 11.2 by our Vmax 0.107. Again, we need to wait for docking to happen, so that will happen as well. So Dmax I can't actually set yet, and de-docking I can't come up with either, because we need to wait until that happens within our sample. So let's look at starting us off then, and we'll go around and just do some checks before we get on with things. So at the moment we have our pressure controllers running. That's good. We have our back pressure, our cell pressure I should say, open. We have our back pressure valves shut all the way. Yep. Our pore pressure transducer is open, so the pore water pressures will be measured during shearing. Our load ram is set in the correct position, or our load cell is set in the correct position, and our LVDT here is also set in the correct position. So as far as I'm concerned, we're ready to start shearing. So with the speed set and the maximum displacement set at the absolute maximum stroke, 21 millimeters, for now. I'll come and change that as we go. Let's start shearing our sample. So I've clicked frame up there, and you can see the force change, and the displacement will start to change as well there. Good. This change in force is the ram overcoming both friction and the pressure of the cell, trying to, as you insert the load ram, and its mass and its volume is needing to be displaced against the volume of water inside the cell. So the load ram is also picking up some force there. So what I'm going to do now is I'm going to cut away, and I'm going to set up the camera on this mount here so that you can see shearing take place, and I'll be monitoring it as it goes, and you'll probably see me come over and in the background edit something on the computer. That's me changing Dmax and from our value of de-docking, finding out what our displacement is after docking takes place. I may not ever actually know exactly what this value is, and you can see here that load, or the load ram and the top cap are actually quite far away. So it will take a fair amount of time for the two to come into contact and actually be seated correctly so that our sample is shearing in the correct manner. But we've got, the time is 10:05, so we'll find out in a few hours perhaps how we've got on. So I'll cut away now, and you can watch the footage of the sample shearing. I'll put it on a nice hyperlapse and speed up, so you don't have to wait around for as long as I do for this to happen. So we'll be back. Okay, so the sample finished shearing after about 2 hours, and you can see, you saw in the video as it was sort of appearing on screen, the sample did shear. There seems to have been a slip plane, a shear plane form. You can see the bottom of it just on the side of the bottom pore stone there, and the top in the sort of top third of the sample. Realistically, there shouldn't be any slip plane or shear plane form over the pore stone. It shouldn't be in contact with the pore stone. That could just be with a problem with how the samples are made, perhaps the fact that the load wasn't being applied perpendicular to the top cap towards the start of the test, as we talked about, the docking phase. Those are just some of the issues that you have when you're doing experimental work. Stuff doesn't always go to plan, and so generally speaking, if you were trying to find out strength parameters of a soil that you didn't know about, you do many tests to get a good average on your soil parameters and try and work some of the issues, experimental issues out like this out of your work. So what we need to do now is start to dismantle our sample and to cut the sample out of the membrane and get it into, weigh it, and then get it into an oven to find out our final voids content. And from a final voids content, then you can work backwards and find your initial voids content and the voids ratio all the way along your consolidation curves. So then you can plot your critical state framework. So let's begin to dismantle this. I will speed up through this. I'll set it to fast forward because this can be quite a long process, but we'll walk you through all the steps, and occasionally I'll slow it down and just talk about what I'm doing. So let's get on with that. The first thing to do is to take the LVDT off the top of the cell. And then we'll raise the load frame up. So we've got the load frame up above our clear of our cell. We need to reduce the cell pressures inside the sample, inside the cell, so that we can take it off and then drain out the water. Currently the cell pressure is 883 kilopascals. With the back pressure valve shut, when we decrease the cell pressure, the back pressure, well, the pressure within the sample, the pore water pressures within the sample that currently stand at around 570, 575, they'll go down as the cell pressure goes down, sort of in a reverse B check sort of manner, and eventually the pressures within the sample will go into suction. We need to wait until, we need to get the pressures down to around 0 so that we can take the PPT off and we avoid damaging that. So that's what we'll do next. So I like to do that in stages, just as you go down, rather than collapse the cell pressure all the way down to close to 0 in one go. I like to just take it down in steps, just so we can keep an eye on the behaviour and make sure it's not doing anything too strange. So now we've got our pore water pressure sitting at around 1, 2, cell pressure sitting around 1. So what I'm going to do now is close off the PPT valve, so that the PPT within here, inside the PPT, there's only a pressure of 2.28, and then I'm gonna release the other side so the PPT is exposed to air. and then I can remove the PPT, and you see a bit of water comes out there that was just trapped within the PPT, but that's absolutely fine. So next thing to do is to start closing off the rest of the valves, that being the cell pressure valve, and then we can also reduce the back pressure controller, as well as as we have done for the cell pressures. Again, the sample's closed off now, so all the water inside the cell and inside the sample is sealed, as we have all the valves closed around this, so we can safely turn down the back pressure on the back pressure controller, so that we can start taking some of these line fittings off. And you can see there the back pressure's quickly fallen down to 0, as the lines were. The pressure change only needs to occur in the line, so it happens quite quickly. So now, if I take these off, so now we have our back pressure lines removed. We've got our cell line removed as well. I can pull this out. There we are. It's also handy to keep some paper towels around when you're removing some of these lines, because they are obviously filled. I'll come back and do those in a second. So now we have our cell just sort of sitting on the load frame. Let's go and just prepare a desk or a station on the bench over the other side, and then we can look at dismantling the cell. So I'll be back in a second. Okay, and the sample is now on the bench, and I've got a few things ready to help us out with getting the sample up. I've got a pair of scissors to cut the membrane. I've got a bucket just to pour all of to get all the cell water out into. We've got a tray that we're going to use to put our sample in, and a set of scales there to find our weight as it comes out of the cell. You want to try and make this process as quick as possible to stop the sample from drying out and losing any water content from when you weigh it initially to putting it in the oven. So once you've got it out of once you've drained the water out, you want this process of getting it in the oven to go as quickly as possible. So let's start by getting the water out of the cell. I'm gonna open up the cell valve and release the pressure from the top by opening up this small valve. And you can see what's there once I open these up. Nice. So with the water out of the cell, now we can start to take the top part of the cell off. So I'm gonna quickly swing this arm round and unscrew these thumb screws that hold the, as we remember from the first video, the top part of the cell onto the bottom. And now you can really start to see the deformation that's occurred to the sample without the distortion of the water around it. So let's look at getting this off of its platen. So for the first part of this, and we don't need to be as delicate here over the shape, we just need to get it off and onto the scales quickly. So I'm going to peel back the membrane on the bottom, and all the suction's removed from the sample there, of the pore pressures inside, and it's opened up to the air, because remember it was still closed to these valves. So I can lift this membrane back over. It's quite a fiddly job with the silicone grease on it still. And we can take the top cap off and the O-rings. So now I need to cut the membrane. I think I'll remove the pore stones first, that's an idea. The filter papers will come. So nice and easy, I'm going to just make a cut down the side of this membrane. You can see that sample starting to close. I'm losing a bit of soil on scissors, so I'm just a bit careful. Not this, you can sort of stuff it. So there you see the sample really has changed in appearance since it went in, since we looked at the sample before, or a sample similar since before it was made. So I'm going to quickly zero this and record the weight of our sample. It's often said in the standards to take a few images of the sample to show its deformation. The slip plane isn't terribly easy to see, but you can sort of infer from its, you can see there as it's come through the bottom of the pore stone. Let's take another one from that direction. So that's going into the oven at 145.9, and we should, yeah, that's fine. So we can leave this in the oven for a day, and once it's out and all the water's evaporated out of it, then we'll have an idea of how much water's flown out of our sample and find the water content at the end of testing, and then we can work backwards, as I described earlier, to try and find out what our final voids content is, and we can move all the way back and find out what our voids content was at the start of consolidation. So that's everything done for as far as shearing goes. So let's just cover where we've got to. If we look back at our board, we see we've done saturation, a B check, consolidation, and then an undrained shearing test, where we think we've reached the critical state. We'll dive into that next time and have a look at whether we reach this critical state assumption of constant pore pressures at continuous strain. We've dismantled our sample, and we're on the way to finding our final voids content, and now it's time for cleaning up, and sorry to say you won't be able to watch that as well. So thanks for watching this one and the series so far. We'll next time probably look just a quick video at how to go through our data and see if we've got anything interesting, and see if it fits at all with our critical state frameworks, or perhaps anything similar to the kaolin samples or the pure kaolin samples we did last year. So thanks for watching, see you in the next one.